Extrinsic semiconductors, that is doped semiconductors. We have seen that you can fine tune the conductivity, or you can modulate the conductivity of these semiconductors by adding impurities. So you can that way, you can increase the electron concentration or the hole concentration without affecting the other. So that was the beauty of it. That was the main beauty. That one thing is you can increase the conductivity. Second thing is you can selectively increase the electron or hole concentration without increasing the other. Because whereas in intrinsic semiconductors, the carrier concentration, they have equal concentration of electrons and holes. That was the problem with the intrinsic semiconductors. Whereas in extrinsic semiconductors, you can selectively, so you can always talk of majority and minority carriers, etc. Because you will see that there will be a class of devices based on minority carriers, injection, and things like that, popularly known as the PN junction devices. So we'll see in the second, third unit, we'll be discussing about that. So there, these things will become important. Right now, it may not be very clear to you why we are all doing all these things, why we want to increase the concentration of one carrier without increasing the concentration of other carriers, and things like that. Yeah. So this is what we have seen. So we can see that if you add silicon belongs to the fourth group, and if you add a small quantity of uh, fifth group element, then we can see that an extra electron is created. So we can again further see that these impurities produce energy levels within the forbidden band. That is the very important point you have to remember, because we will be going towards the energy band diagram with intrinsic semiconductors. Energy band diagram we have seen. You have the conduction band, you have the valence band separated by the forbidden band. Then in the middle you have the Fermi level. Now, when we talk of the extrinsic semiconductors, again, you have the conduction band, you have the valence band, and then you have the forbidden band, and then you have the impurity levels. So impurity levels, if they are providing electrons to the conduction band, so they will be very close to the conduction band. And if they are providing holes to the valence band, their impurity levels should be lying very close to the valence band. So that picture we should keep it in mind. So that is one point we are going to discuss. So that is why the right hand side in the diagram you can see that the donor levels, you can see it is shown multiple levels. We'll see that it is not multiple level, single level for here. Just to, it can be, we'll come to that details little later. So one thing important you have to understand is they form a level very close to the conduction band or very close to the valence band, so that they can give electrons to the conduction band or holes to the valence band. And mind you, the hole's energy increases downward, whereas because basically this y-axis in this energy band diagram is the energy. So when you go up for the electrons, the energy increases, and when you go down for holes, the energy increases. So that is what you should keep it in mind actually. So the gap between the conduction band edge and the impurity level shows that what is the energy required to liberate an electron from the impurity level to the conduction band. Similarly, the gap between the impurity level and the valence band gives the energy required to liberate a hole into the valence band. So those things are important things, so that we should keep it in mind. So this is first, this diagram is about N-type. Similarly, we can talk of the P-type material. So as I said, these impurity levels below the conduction bands are known as donor levels, because they are easily donating electrons to the conduction band. and this they will be carrying the electric current and things like that. They will be the carriers for the electric current. So in the p-type, so that means you will be adding a third group element. Then you have acceptor levels. So they accept electrons and give out holes. So they are known as acceptors. So they form energy levels very close to the valence band, and donors were very close to the conduction band. And so it should be away from the middle actually, so that it should be either close to the valence band or close to the conduction band. Depends whether it is P or N. So in the case of p-type impurity, see for example, it is a gallium is shown as the impurity here. You can it is going to accept electrons and give out holes. So this is the picture. So this is what I wanted to show. This is a better. So when you're drawing the band diagram of an extrinsic, of course, Fermi level is missing in this. But when you draw the energy band diagram, these are the things you have to show. Of an extrinsic semiconductor, you will be showing the conduction band edge, you will be showing the valence band edge. Then if it is n-type, you will be showing the donor level. And if it is an acceptor or p-type material, you will be showing the acceptor level. And very important, or this acceptor levels or donor levels are not continuous, they are discontinuous. To show that, this is very important, because as I told you in the very beginning, doping is about adding a very small amount of impurity. If you, I don't know whether any of you have worked out that problem. If you work out that problem, you will see that the impurities added percentage wise between the host and the impurity, there is many orders of difference, actually 3-4 orders of difference between the host and the impurity. Then only we can talk of a doping. Otherwise, generally we talk of alloying or alloying kind of thing. So here, this is very important. That means it clearly shows that there is no interaction between the impurities. Impurities and the host, there is an interaction, but impurity interaction is ruled out. To show that in the band diagram, we are showing them as a discontinuous lines, because see if you see here the last diagram, you see, I don't know whether you can see this. One gallium atom is sitting here, then another gallium atom is sitting. There is many atomic distance between this gallium and this gallium. There is no interaction possible between these two gallium atoms. So that clearly shows in the. Similarly, in the case of p-types also, it is. Where is the arsenic? Yeah. So here only one arsenic atom is shown. There can be, they see here another one. So you can see that there is many atomic distance between them. If there are a lot of arsenic atoms, then our that assumption is not valid. So there will be consequences of that. So when we talk of normal doping, this is the situation. The interatomic distance between the dopants are very large. So there are different ways of saying the same things. That the atomic percentage of the dopant is very less as compared to the host actually. So it will be good to see if you can work out that problem which I gave you, that we can see that the atomic percentage is 3-4 orders of different. And again, one more thing we have to understand, this probably we may not have discussed, this impurity level, because we have seen that in the donors are basically from the fifth group. There are many impurities from the fifth group. So each will have different ionization energy. See, for example, phosphorus, it is, or there is another table where I will be clearly showing. So this gap is about 44 MeV, milli electron volt, whereas the silicon band gap is 1.1 electron volt. So normally to create an additional electrons, you have to give 1.1 electron volt, whereas because that is the beauty of this band diagram. This band diagram clearly shows that in order in an intrinsic semiconductor to create an additional electrons, you need energy of 1.1 electron volt, whereas in the case of an n-type semiconductor, to create an additional electron, you need, if you are talking about the phosphorus, then it will be needing only 44 milli electron volt. So you see the big difference. Similarly for arsenic, so this is only again, you can see that it is 54, and all you can see that more or less in the same range. Actually, the energies, donors and acceptors, it is more or less same orders of, that is few MeVs, and you can work out that it is of the order of thermal energy, room temperature. This can give that much energy. So at room temperature, most of the donors and acceptors will be ionized. So this is this gives you an idea. So so before going into further, one thing I just wanted to mention, that this is again, we are going back to intrinsic semiconductor a bit, because in the band diagram, in this band diagram, I have not shown the Fermi level. So where will be the Fermi level in the case of intrinsic semiconductor? So we can show that in the case of intrinsic semiconductors, this is a proof. It is at the middle. So we can see that actually, because in an intrinsic semiconductor, N0 and P0 are equal. So if you go back, we have already shown that, I am not written it again, that equation, you will see that what are the fact, n into P is Ni squared. So from that we can find out N0 and P0. And so if you equate N0 and P0, this will come, and then we can show that from this, if you work out for EF, you will see that it is half of EC plus EV. That means it is in the middle of the band gap. So this is a very important relation. So that the Fermi level, intrinsic Fermi level, will be in the middle of the forbidden gap. So that is the intrinsic Fermi level. Because whenever we draw the band diagram, these are some of the things we will be showing. One is the conduction band edge, then is valence band edge, then intrinsic Fermi level, it will be in the middle. And then if it is a n-type impurity, you will be showing the donor level. Then we will be seeing that there will be Fermi level correspond to the doped semiconductor. That is, we will be calling as ENF or EN. That is the Fermi level of the n-type. It will be very close to the ED, but then that is different actually. That is the Fermi level of the n-type material. Similarly, you will be having a Fermi level of the p-type material. So these are the things we should remember: the conduction band edge, the intrinsic Fermi level, then the impurity level, whether it is donor level or acceptor level. And then, so very often we may not be showing this impurity level. Instead of that, we will be showing the Fermi level only. So basically, the conduction band, intrinsic Fermi level, and the Fermi level corresponding to the dopant. So that is n-type EFN and p-type EFP. So that is what the general band diagram will be having all those. So this is a proof that it is in the EI will be in the middle of the forbidden band. So EI will be shown like this. Now, this is what I saw, some of the properties of impurities. This tetrahedral radius means it is about the unit cell we are talking of. You don't have to, in crystallography, that unit cell will come. Anyway, you don't worry about that. So, but interest is the misfit factor. Already I have discussed in the last class. You can see that arsenic has a misfit factor of 0. And most of the other, phosphorus also has a very low misfit factor. So these are the misfit factor of various other impurities which are incorporated in silicon. So this is, and then you see, this is not a distance, actually it is the energy gap. So you can see that this is a kind of energy. So this is a kind of energy. Like there is a slight difference. The arsenic has 0.40 electron volt, then phosphorus has 0.044, then antimony has 0.039. These are the n-type dopants, and this aluminum, boron, gallium, etc., has different uh, ionization energies. Or this is the, we can say that the gap between the impurity level and the valence band or the conduction band, depending upon the type of the impurity. So you can see that actually. So some of these metals will have different energy. They may form different states. All this, one thing we have to keep it in mind. All this form gap, or all these form energy levels within the forbidden band. So that is very important. Now, I told you in the beginning that there is no interaction between the impurities actually. So you have a shown uh, discrete lines or discontinuous or dotted lines. We have shown the impurity levels by dotted lines. Now, one may ask, suppose you go on adding impurities, and of course, you know that you can go up to solid solubility limit only. So when that such cases, when large number of dopants are involved, will the situation remain the same, or what do you expect? Suppose very large dopants, concentration of dopants are introduced, of course below the solid solubility limit, then what happens? Any idea? Hello? Hello?
Yes, sir.
Yeah, what happens if you go on increasing the dopant concentration and that, but below the solid solubility limit? Anything, any change in the behavior you expect?
So it will again come to the
Pardon?
intrinsic.
Yeah.
It again going to become intrinsic.
No. So actually, what happens is we are coming to that point. This is sometimes this becomes important actually. So this such semiconductors are known as degenerate semiconductors. Normally, if you go through any textbooks of semiconductor physics, always they will be giving one assumption. They will say that assuming that the semiconductor is non-degenerate. Non-degenerate means it is lightly or moderately doped. So these are, see, three terms are very often used as far as the doping is concerned. You should be very careful. That is, of course, a relative term. Very often we talk of lightly doped, we talk of moderately doped, other one is heavily doped. So typically around if the per unit volume it is of the order of 10 raised to 14, then we say it is lightly doped. Then if it is, I mean, typical, these are not, there is no hard and fast rule. But if it is around beyond 16 and below the solid solubility limit, like 10 raised to 17, 18, then we say moderately doped. Beyond that, like it can go up to, okay, in the case of phosphorus, it can go around 19, 20, almost 10 raised to 19 to 20. That is the solid solubility limit. Then we say it is heavily doped. So these are the three terminologies we use as far as the doping is concerned. I mean, loosely used. One is lightly, moderately, and heavily. So if it is heavily doped, then we say it is a degenerate semiconductor. So later on, we'll be seeing one thing. When we, as far as the energy band diagram is concerned, we have seen that intrinsic Fermi level is in the middle. And so when you the dope it with n-type impurity, the Fermi level will be shifting, or the Fermi level of the n-type material will be very close to the conduction band. And similarly, when in the case of p-type material, the Fermi level will be very close to the valence band. Now, for a degenerate semiconductor, what will happen is the Fermi level will go into the conduction band or into the valence band, like metal. It becomes behaves like a metal, or as popularly known as the semi-metal. So the semiconductor becomes metal-like because the Fermi level has gone into uh, either into conduction band in the case of n-type, and for p-type it goes into the valence band, because steadily it will be going. We'll be doing some numericals on this, that as you increase the doping density, the Fermi level will be shifting away from the middle towards the conduction band or towards the valence band. So that is why the name, that is, the semiconductor has degenerated into a kind of metal or a semi-metal behavior. So this is very important. And another consequences of this is there will be interaction between the impurities. So you cannot show it as uh, dotted line. So there will be interaction between the impurities. Another important thing is your band edges. It is as if the band edges have come down. That means the band gap is reduced. So all those things happens actually. So you will be seeing a reduction in the band gap. You will be seeing the Fermi level going into the valence band or the conduction band. So you can have the degeneration of the semiconductor taking place. And then another important thing is we have so far assumed that the distribution law, even though we said that electrons are fermions, we have said that we need not worry about Fermi-Dirac distribution because the carrier concentration is not very high. We can use the Maxwell-Boltzmann statistics. But for a degenerate semiconductor, we have to use Fermi-Dirac statistics, not the Maxwell, because the number of carriers are also more and number of states are also, I mean, they are in unit, I mean, like they are all nearly same. So these things we have to keep it in mind, because very often we come across situation where the semiconductor could be approaching degenerate cases. Some because for making ohmic contact, and some cases we do heavily doping. So there things can change. For again, when we go into the BJT, we will see that emitter region of the BJT is heavily doped. So those, in such situations, there can be issues, and the basic, there could be changes in the physics taking place actually because of this change in the energy band diagram. That is why I am bringing in this here. So when we discuss about the BJT, we will be discussing some consequences of this. But right now, I just want to tell you that the semiconductor can degenerate if into a metallic behavior, or the behavior changes when we have heavy doping. So that such semiconductors are known as degenerately doped semiconductor or degenerate semiconductor. Then another kind of semiconductor, which is known as the compensated semiconductor. Have you heard of compensated semiconductors? Yeah.
No, sir.
Compensated, what do you think it should be? Or what is it? Compensation? No, any idea? What is the meaning of compensation? Yeah.
When something is given, when some loss is incurred.
Yeah. So here what is happening is, see here what is like here also it is that is a situation. Let us see. So what is happening is, so you have, see, for example, you started with an intrinsic semiconductor. Now we introduced donors. So a certain number of additional electrons or additional excess electrons were created. Now we can compensate for those electrons by introducing additional holes. So what you can do is you can introduce acceptors. So then if all the electrons are compensated, additional electrons which are created by that doping is compensated by the additional holes created by the acceptors, then we say it is a compensated semiconductor. You see, there is a difference between a compensated semiconductor and an intrinsic semiconductor. It looks same because now the carrier concentration is same. Electron and hole concentration will be same that way. But it is a doped semiconductor. So that is a difference. Very often we see that there are applications where you need intrinsic or high resistivity. Normally, it is not the pure intrinsic material we use. Normally, very often we go for this compensated semiconductor, because as such the wafer comes with a prior doping during the Czochralski growth. you intentionally, very often p-type, earlier days, the bipolar technology, it was p-type, or p or n-type is incorporated. So normally the semiconductors with comes with a certain amount of doping. So then what you, in order to make the p-type, n-type, first you will be compensating it and then go to the n-type, or similarly, if it is the other type, then again you compensate and things like that. So this is another important term very often you come across, that is compensated. And see, for example, one example I can think of is this pin diode. Have you heard of pin diodes? Pin diode.
Yes, sir.
What is a pin diode? Where is it used? What is pin diode? Yeah. Yes. What is pin stands for?
The
Yes.
middle region is intrinsic.
Yeah, it is actually, it is supposed to be intrinsic, but very often it is a compensated semiconductor. Actually, it won't be a pure intrinsic material. So it will be very often if you have a kind of compensated semiconductor where the electron and hole concentrations are equal. That way they resembles the intrinsic. Very often pin diodes are made like that. It's not a pure undoped semiconductor. So this is one example. Pin diode is quite popularly used in optical fiber communication systems for because of its large sensitivity and all those. So those details you'll be studying in your optoelectronics paper. But this is like compensated semiconductors are important. So you are cancelling uh, a certain amount of excess electrons given by the donors by adding acceptors. So that is the idea of it. Yeah. So this the detailed band diagram, etc., associated with that is shown. It is understandable here. The important thing is the donor and the acceptor concentrations are same, so they are cancelling out. So that is the idea. So of course, it won't be a degenerate semiconductor. It is moderately or lightly doped semiconductor. Very often, it is a lightly doped semiconductor. Yeah, this is another kind of term associated with the doping. Yeah, so we will see some other additional terms which are used in the case of extrinsic semiconductors. You should be, I want to make you familiar with these terminologies. So one is the shallow level impurities. Heard of this? Have you heard of this shallow level impurities?
Yes, sir, like gold or silver.
Pardon?
Sir, like gold or silver.
Shallow. See, actually, shallow and deep comes from this, actually. So you see, this donor level is coming. You can see this diagram, no?
Yes, sir.
Yeah, this is your conduction band edge, and the impurity level is very close. So it is the depth is very low. So it is very shallow. If you come from the conduction band to a donor level, similarly, if you go from valence band to this acceptor level, the depth is very. So this is an example of a shallow level. So all dopants, whether it is donors or acceptors, they form shallow level. Whereas if they form levels towards the middle of the band gap, so you can see again, probably you see that 8 9, you see it will be towards 1.1 is the middle, so it is very close to the one side. So then 0.1757, so these are towards the middle, so they are known as deep level. So you can see that these metallic impurities, this has consequences actually, like gold, copper, molybdenum, etc. Molybdenum, of course, nickel, all those things, they form levels very close to the middle. So they are known as deep level. So that is what there are two kinds of dopants. They are so shallow level impurities are normally all the dopants are shallow level because they are providing electrons or holes to the conduction band or the to valence band. So other name for impurities are shallow level impurities, and the level they form is shallow level. Whereas deep level impurities means that they create levels very close to the center of the band gap or deep states. So they very often act as we'll see again, it is very important in PN junction devices to control the lifetime of the minority carriers. So they can act as traps. So again, when we discuss about BJT or PN junction devices, these things become important. So there is a deep level. So they can act as traps for charge carriers and reduce the conductivity or the very often we use it for controlling the time. So these are the two kinds. And another important thing about deep level impurities are they are normally interstitial impurities. Like gold is a classical example. They are examples of they go to the interstitial side, whereas these dopants, normal dopants or shallow level impurities are substitutional. We talked of substitutional impurities and interstitial impurities. Most of the deep level impurities are interstitial impurities, and some of them go into the substitutional sites also, but most of them go through they lie in the interstitial site. They don't they most of the time they won't be providing any additional carriers. Only thing is they can interfere with the carrier transport. That way we call them as traps or recombination senders and all those things, because they will be facilitating the recombination of electrons and holes, which is very important in minority carrier operated devices. So those kind of control is possible with this deep level. So apart from conductivity modulation, we can see that doping can be used to control the lifetime of the carriers. So these deep level impurities are very often used for that. So have you heard this name, third one, electrically active dopants? Yes, electrically active dopants. Yes, yes, no.
No, sir.
So actually, the electrically active dopants means the dopants which give carriers. They give additional carriers, whether it is electrons or holes. So shallow level impurities or donors or acceptors are known as electrically active dopants. They are expected to give. So very often it may not happen that if you are adding N phosphorus, we are expected to get N additional electrons. Similarly, if you are adding N borons, we are expected to get N holes additional. So such dopants are known as electrically active dopants because they are adding additional carriers. So this is another name very often used for acceptors or donors. Then the term this amphoteric dopants. Have you heard of amphoteric dopants? Yes.
Sir, which can act as
Yeah, this
both
is very interesting.
donor or
So like amphibians. What is amphibian?
sir, like frogs, which can live in water
Yeah,
and
there are
on
some
land.
animals which can live in water as well as in the on earth. Like frog is an example. Like tortoise or many other amphibians are there. So this here, amphoteric means it can act as both as a donor as well as an acceptor. So one example is again, if you go back to this, that time I didn't want to bring your notice. Gold, you see, gold has two levels. One is towards the middle. So it's slightly below, close to the valence band, and one is above the. So it can act as both acceptor as well as donor in a case of silicon. So of course, they are not electrically active, but gold is one example of an amphoteric dopant. But one of the most commonly shown example of amphoteric dopant is silicon as a dopant in gallium arsenide. Gallium here, don't misunderstand. Silicon is used as a dopant actually. So you have gallium arsenide, the semiconductor gallium arsenide is the host. So if gallium arsenide in the gallium arsenide, if silicon gallium is replaced, then it will act as N-type. If it is arsenic is replaced by silicon, then it becomes P-type. So this is a kind of amphoteric dopant. So this is another example, classic example, depending upon the various activation energies, etc. So gold in silicon can act as an amphoteric dopant, and silicon in gallium arsenide. So this is one dopant for the gallium arsenide, where it acts as a amphoteric dopant, depending upon what is it replacing, gallium or arsenide. Because there are two choices there in the case of gallium arsenide. Either you can replace gallium or you can replace the arsenic. Then we have already discussed degenerate and non-degenerate semiconductors, uh, because we have seen that heavily doped semiconductors are known as degenerate semiconductors, and very often most of the physics will be around non-degenerate semiconductors. So very often we will assume that the semiconductor is non-degenerate. Whenever we talk of an extrinsic semiconductor, keep it in mind, there are only special cases where we will be going into degenerate because the physics changes. So the model we are developing is mostly for the non-degenerate semiconductors. Then of course we have seen the difference between compensate semiconductors and intrinsic semiconductors. Now let me ask you one question. Suppose you have silicon and you have certain conductivity. Now I introduce the dopants and it is a compensated semiconductor. Will the conductivity same? You try to understand the question. You have an intrinsic semiconductor. That means electron and hole concentrations are same. Now we are adding dopants, both equal number of acceptors and donors. So again, the electron and hole concentrations are same. And what about the conductivity? Will there be any change in the conductivity? Increase, decrease, or it will remain the same? Which will have a higher
Same.
conductivity? Yeah.
Sir, I think same.
Same conductivity.
Let us take a poll. How many agree with this that the conductivity will be same?
I think
Same.
different.
Yeah. Next, Prashant is there.
No, sir.
Yeah. So anybody else? Everybody has given their opinion. Now let me ask Bhaskar, why you said it will be different? What is the reason behind why it is different? Because normally we will expect that it will be same, but why you say that it will be different? Because that is the obvious thing was to say that okay, it will be same. But then why you said it will be different? What is your argument, or what is your justification? Yeah.
And know the formula of sigma is equals to
Yes. Hello. You got my question?
Sir, sir,
Yes.
his mic is on, but he is not speaking, or we cannot hear him.
I am also not able to hear him actually. Yeah.
carrier.
Yes. Pardon?
We actually increase the carriers in the compensated case.
Yeah, but then the number is same. Yeah.
So, but what about the uh,
Yeah. See, we need to understand one thing. We need, of course, the carriers are increased, but there is a change in the mobility of the carriers because the conductivity is decided by two factors. One is the carrier concentration, and the other one is the mobility. So, what will happen to the mobility? Mobility also will increase or decrease?
So decrease.
Yeah, this also we need to take into account actually, because when we have a compensated semiconductor, even though the carrier concentrations has increased equally, like electrons and holes, but there will be a decrease in the mobility. So you don't expect that kind of course there will be definitely a change in the conductivity, but the conductivity increased will not be proportional to the increase in the carrier concentration, because there will be a decrease in the mobility actually, because so that way for the same carrier concentration you will not get the same conductivity, you will be seeing a decrease in the conductivity because of the mobility decrease actually. That we have to keep it in mind. So this is that mobility decrease we need to consider actually, because the impurity scattering is, because we have seen earlier, mobility is decided by scattering. So impurities will introduce additional scattering, especially at low temperature. So that becomes important. So they will contribute to the conductivity. Yeah. Now, have you heard this term freeze out? So again, it is used in
Yes,
the
sir.
context of doping actually. Yeah. What is it? Freeze out?
So when we increase the
Increase the.
level, the carrier got filled out.
See, actually, we have seen that even though the energy is very small, there is a certain energy is required to ionize the dopants, whether it is N type or P type. Certain amount of energy. We have seen that it is lying in the range of milli electron volt. That much energy is required. If you suppose that energy is not there, can you tell me a situation where that energy is not there? You got my point. So we have seen that a certain amount of energy is required to release an electron from the donors or from a hole from the acceptors. So now, suppose that energy is not available. Can you tell me a situation where that energy is not available? Anybody? Hello?
Yes, sir.
Yeah. When is it possible that that energy is not available and it is not able to give out electron? Is it possible?
Sir, non-metals.
No, we are talking about the semiconductors, like doped semiconductor. You have a silicon. We have seen that is the energy. And can you imagine a situation where that energy is not available and the carriers are normally we take it for granted that the all the see, if you are adding 10 phosphorus atoms, you get 10 additional electrons. But can you imagine a situation where that kind of that situation breaks down? That's what I'm asking. So, in order to understand this, we need to understand from where that phosphorus is getting energy to liberate electron. From where it is getting. Normal case. From where it is getting the energy for ionization. Yeah. Any answer?
Sir, the chemical energy.
No, it is the thermal energy, because room temperature, you can calculate actually. You take the value of Boltzmann constant, thermal energy can be at any temperature. Thermal energy can be, you should do a very good exercise. You can take the Boltzmann constant and then multiply it by T at any temperature. For example, room temperature, you will see that it will be much, the thermal energy will be much more than the energy required to ionize the phosphorus atom or things like that. So because we have seen
Oh,
that they are lying in the MeV range.
so sir, they freeze out when the temperature is not
Yeah,
enough.
temperature is low. When the temperature is low, much below the room temperature. So where the such a situation is possible, where the kind of that kind of temperature, low temperature, it's a very we talk a low temperature is otherwise known as cryogenic condition. Have you heard of cryogenic condition?
Yes, sir.
Yeah,
Yes.
cryogenic means low temperature. Very often, space, when you are having extraterrestrial missions, like you are launching your space vehicles, satellites, then you have your other space labs, and going to your other planets, or going to other satellites like moon or anything, all those missions, there the temperature can go down. Of course, there are provisions should be provided, but this cryoelectronics is becoming very important as far as the space applications are concerned. So there, the impurity freeze out has to be taken into consideration. So under cryogenic conditions, you have to, so there, instead of cooling, you may have to, of course, high temperature cases, you have to do the other one. You have to cool it, because you have seen that semiconductors are sensitive to temperature. So the reverse also is possible. Under very low temperatures also, semiconductor can behave, and even the impurities may not be ionized. So you need to heat it, or suitable precautions has to be taken. So such situation is known as freeze out condition. So this is very important as far as the space research is concerned, or space applications are concerned, where impurity freeze out situation should be avoided. So these are some of the terms which we come across when we talk of the doped semiconductors. So very often we may not be we may not have come across these things, but it will be a useful thing to know all these things. It's not very difficult to understand, because most of them are self-explanatory, like shallow and deep, then electrically active, amphoteric, non-degenerate and degenerate, compensated, then freeze out conditions, etc. So these are the some other terminologies which we very often use when we come across the doping. Now, now we need to see. So far, we have been developing the theory of the extrinsic semiconductors. Now we need to know what will be the carrier concentration for the extrinsic semiconductors. We have seen that in the case of intrinsic semiconductors, we have seen, and then we have invoked the law of mass action. Now we will, and then what is the energy band diagram and all those things. So now we will be developing that. So that I will be taking up in the next class, and then where is the Fermi level for the doped semiconductor. Those aspects we will be seeing. So before closing today's discussion, two things I would like to do. One is, if you have any specific questions regarding what we have discussed today. And second thing is, of course, I am going to give you some work to carry home, where you can work out those things. So first I will pick up the questions from you, if you have, and then we will go to the my questions.
So,
Yeah.
sir,
Yeah.
sir, I want to ask about Fermi level and deep level impurities.
Yeah.
Uh, sir, so if the deep level impurities of P type, so Fermi level is about at the same position where donor level is there.
No, actually, deep level impurities, it will be deep level means they are lying deep into the forbidden band. That means towards the middle. Got the point? So deep level impurities will be lying with, because if it is coming close to the conduction band, you will say it is a donor level or shallow level. If it is coming close to the valence band, you will call it as acceptor level. So the middle one will be the deep level. If it is exactly in the middle, you will say the most middle, actually most deep. Actually, you got the point.
Yes, sir. Yes.
Yeah. So deep level impurities which are lying towards the middle, they will be as close to EI, actually intrinsic. They will form as close to the intrinsic
Mhm.
Fermi level, and we'll see later on. Many of these, you will see that deep level impurities are treated to be at the intrinsic Fermi level, or very close to that, actually. So their Fermi level will be towards the middle only. So the
Okay, sir.
deep level impurities form levels towards the middle of the band gap. Like gold is one classic example, iron is another example, which is commonly used in silicon, because the advantage of gold is, the diffusion constant of gold is very high, so it can be diffused very fast into silicon after all the processes are done. Actually, the back diffusion is done in BJT. like from the lower side, you can do the diffusion after your, because normally you need it in the collector base region, so you can diffuse it from down. So normally in the planar technology, most of the processing is done from the top, but in this case you can do it from the back. So deep level impurities will be lying towards the middle. That answer your question?
Yes, sir.
Yeah. Any other question? Any other questions? So then let us look into some of the questions I have prepared, and it's not very exhaustive, but some of the things which gives you adding to the. So earlier I said that Fermi level will be lying for intrinsic semiconductor. The Fermi level will be in the middle of the band gap. Now you have to show that it is not exactly in the middle. You have to prove that it is not exactly in the middle. It's slightly above the middle. So that proof is you have to work out the problem. I have given the derivation showing that it is in the middle. So there I have made one approximation. So if you eliminate that approximation, then you will see that it will not be in the middle. So you have to go through my, and what is the first you have to find out what is the approximation I have made, and then you will be, and then again solve for the Fermi level, then you will get the result actually. So that is what you have to do. You got the point?
Yes, sir.
Now, yeah,
Yes.
similarly, yeah, you want to say something?
No, sir. No, sir.
So again, another one is you have in N type and P type, you try to find out the Fermi level. And you show that depending upon the doping density, the Fermi level will be shifting upward. For example, N type semiconductors. Just 1 second. You can have a look at the question. I will come in a minute. I have some guest, I think.
बच्चे आए हैं.
Yeah, have you seen the questions? Hello?
Yes, sir.
Yeah. So this second question you try to do, otherwise we'll discuss this proof. Again, all these are quantitative questions, or you can do it quantitatively. The first two. Then the third one. This is one of my all-time favorite question. So I hope you understand the question. See, actually, if you take a phosphorus atom, for a phosphorus atom, if you want to liberate an electron, the energy required is much higher, like of the order of few electron volts, actually, much more than the band gap energy even. So whereas in the case of phosphorus in silicon, the requirement is, you have seen, it is of the order of few milli electron volts only. So you can quantitatively prove it. I'll be very happy if you do that, or at least qualitatively if you can tell me what is happening. Yeah. Any idea? Or you want some time to think? Next time you'll give me the answer. Anybody has any answer?
Next time, sir, we'll
Sir,
give the answer.
Yeah. Somebody wanted to say something. Let me hear.
no, I don't. I'm not sure, sir, but um, it is related to sharing of atoms and.
No, it's not sharing.
Okay, so then I will think and
Yeah. So anyway, this is the last question. Already I have asked you, but still you can think about over it. Uh, so I need not, because it's about the intrinsic and the compensated. So it will be a good exercise if you do all these questions, and which I have given earlier also. So probably we will take up those some of those questions in the next time when we meet, probably on Saturday. And then we will be quantifying what about the carrier concentration of doped semiconductors, and we will again invoke the law of mass action and etc. So that is kind of some of those equations will be involved. So that is what we will do in the next class. So I think if you don't have any specific thing to discuss, so we'll stop it here today. Is it okay?
Yes, sir.
yes.
Huh?
Thank you, sir.
Okay.